All right. So now we are going through the normal forms and what it is. Normal forms is very beneficial, especially because of the let me see, of the redundancy that can happen in your database. So when you have a lot of data already, imagine very large database, and if you have any redundancy there, it will actually slows down the database, and it's the whole thing about normalization is to reduce the redundancy there along with other things. But the most important thing is the redundancy. So what happened with when you have a lot of redundancy? So this is a root actually of several problems. For example, I already talked about the storage, but if you have a lot of redundancy, more problems would arise when you insert the data, when you delete or when you update the data. It would cause anomalies in the database. For example, if you have redundancy, like you have like name associated to department for a student, right? For example, like this student is taking a major in computer engineering. And then when you update this person, for example, this person moves their major and then now changes their major. What happened with that? You have to look throughout every databases or every relations if the information about the major appears in many of the relations. In that case, you have to change in every relation, right? In every row, every tuple, in every relations. But now, if you could minimize the redundancy, it will perhaps save you a lot more time and also make the database correct. Otherwise, it could happen that, the database will come, the data in the table would become a lot of anomalies. So how are we going to make it or make sure that the database here is efficient? We call something functional dependencies. So that is the tools or the mechanism that we'll use in order to identify the schemas, whether or not it has the redundancy problem or other problem related to not of the good design of the database. All right. So today we will talk a lot about functional dependencies. So what is functional dependencies? Functional dependencies by itself, again, as it be used to specify formal measures, whether or not the relational design that we have is good. So it measures the goodness of your design. Now, so the functional dependency is actually one of the constraints. In the past week, we talked about a lot of constraints, but today it's another constraint called functional dependency. But these functional dependencies actually derived from the meaning or what you want to do with your database. So actually, it's the assumptions that you really have to go through the requirements of the database, and then you determine what kind of functional dependencies are there. So it is very much possible that the dependencies that you define may not cover everything at the first place. So you can keep adding or modifying the functional dependencies as you go along. Now, the functional dependencies here that we are going to define along with the keys of the database will actually be necessary to define normal forms, all right? On the normalization process that we are going to talk about in this session as well. So when we do the normal forms or normalization, what we will cover in this class is first normal form, second normal form, third, and then BC and F. But actually, there are a lot more normal forms, but these are the common ones that when you go and work in the companies, most likely they will be talking about these four forms, first, second, third, and BC and F. And most of the time, when you go into a company, they probably say that check whether or not it is in BC and F or in third normal form. But you will have to understand first, second before you reach the third because it's on top of the other. Now, how does functional dependency look like? This is its description. It's a set of attribute X, right? Set of attribute X functionally determines a set of attributes Y if the value of X determines a unique value for Y. So these description might be a bit confusing. So let's take a look at the example. I can say that if you have student ID determines, if you see the symbol here, I use the right arrow. So I'm saying that the student ID determines first name and last name. All right. So it means that if you have one student ID, you have to get the same first name and last name. All right. In that case, we will say that SID determines F name and last name. Or you can say that F name and L name are determined by student ID. All right. So that means set of X functionally determines set of Y here. Right? It could be one, it could be more than one. Now, actually, we are learning functional dependency today, not only because of the uh, normal form, but actually we have to go through many things. So let's see what we will cover. First of all, we talk about the description of functional dependency. Once we have the dependencies, we will compute all of the implied dependencies because we probably could only identify a few, and then we have to compute all dependencies possible in order to define normal forms. So in that case, we are going through what we call F closure, which is all the implied dependencies. And then in order to work on it a little bit easier, we introduce something called attribute closure or X closure, which is actually a more simple way to actually compute all the dependencies there. And then after these, we'll be able to define all the candidate keys for the table. And then once we have the candidate key along with this FD, we would be able to check the normal form from first, second, third, and BCNF. And then we can decompose the relations such that they become normalized. And finally, what the objectives is to our objectives are to reduce dependency and to eliminate the anomalies. All right. So these are the steps that we will be covering today. Now, let's go to the next one. Then how to compute the functional dependencies. All right. And also the F closure. F closure is actually the set of all functional dependencies that can be implied. So let's start from here. Given some of the FD, right? If say that we have functional dependency, I will call it FD. We can usually infer additional FD. For example, if have like student ID implies department ID, and then department ID can let me start again. The SID determines department ID. What I mean is that if you know SID, we are sure that this student ID is in this department ID. So when you have the same SID again, you will always get the same department ID. That is the meaning of functional dependency, all right? And now you have another set, and another set say that for any department ID, the same department ID, you will always get the same location. So it looks a little bit like key, right? But we will talk more about key a little bit, but now we'll call it functional dependency, and we read it as SID functionally determines department ID. Department ID functionally determines location. But if you want to read it a bit shorter, you can say that SID determines department ID and department ID determines location. But now with this, you learn from high school, you know that X determines Y determines Z. Then you can imply that X determines Z. So you get SID determines location. So this is the implication that you can learn. Now, we have a set of FD called F, which is implied by a set of FD, which we will signify as in F, the capital F. So one FD, each of the FD will be signified with small f. And then a set of all FD is a capital F, all right? Now, for to compute F closure, what does it mean? An F closure is the set of all FD that are implied by F. Let me say it again. Small f is just each functional dependency. All right. Small f is one each one of the functional dependency. Now, the large F is all the set of functional dependency that you gain or you set for that particular problem, right? But now, F closure is another thing. You take the F there that you have the whole set, and then you say, are there more that can be implied from what you have already learned? So that is called F closure. Now, let's see the how are we going to compute or learn about the what they can imply further. Okay, so how to imply? We are going to use the Armstrong's axioms. I'm not sure if you still remember from high school or from. I'm not sure if he's in discrete math as well. So we have three rules here, three main rules: reflexivity, augmentation, and transitivity. So in reflexivity, we say that if X is a subset of, if Y is a subset of X, and then we can say that X determines Y or X functionally determines Y. All right. So it's a reflexive, right? Y subset of X, then of course X determines Y. Now for the augmentation, you can see that if X functionally determines Y, then you can add or augment the data, augment the attribute to both sides. So then set xz determines yz for any z. So you actually can augment on both sides. Now, for transitivity, you can say that if x determines y and y determines z, then x determines z. So this is called the transitivity, right? So you can see that the uh, example that I gave you above, where I say SID determines the department ID determines location. So that is the transitivity rule, say that then XID determines location, right? Now, there are more rules that I like to show here, which are union and decomposition. So for union, we say that if X determines Y and X determines Z, then because if X determines both, right, you can union them and say that X determines Y, Z. And you can also use the decomposition rule where X determines Y, Z, then you can do backward and say that, then that means that X determines Y and X determines Z. So these are all the implications that can be used when you compute F closure. So you can see that, oh my God, I only have just a few functional dependencies, but in the world, there are a lot more if you have to compute F closure. But F closure is needed because you have to understand the importance of the each of the data in your database in order to compute the keys afterward. All right. Now I have the example, so I hope that this is easier to see why we need to do it. Let's say that we have a relation called contracts. All right. And within contract, we have contract ID, supplier ID, project ID, department ID, part ID, quantity, and value. And to make it fast to write, like for the lazy one, right? I can say that C, the contract, I'll just denote it as C S P D P Q V here. All right. So it corresponds to the first letter up here. All right. So you can see that in this example, contract ID is the key because it is underlined, right? So we can draw from this that C actually, I mean, a contract ID here determines itself, which is contract ID. It also determines supplier ID. Let me see here. Oops. Yeah. Oh my. Okay. So now C by itself, this is contract ID. So C itself would determines its itself. And it's because it is key, then it determines the rest as well. So it determines supplier ID, it determines project ID, J stands for this project. It determines department ID, it determines the part ID, it determines quantity, and also the value. Because it is a key, then you can draw the functional dependencies that C or the key determines everything in the table. All right. This part is still easy, right? Because it's the key, so it determines the rest. Now, if I have a dependency, another set of FD, I say that project purchases each part using single contract. So I mean that for every project, if I buy, for any project to buy one part, it would have to come up with one contract, with one contract. So it's a single contract. So it means that in one contract, in one contract, it has to have just one project and one part ID, one part. At that, how does this happen? This is just the condition, or it's just a constraint that you put upon into your database design, right? Okay. Now, I also have another functional dependencies that I set for this particular problem. I said that if a department purchase something, it said that department purchases at most one part from a supplier. So if that is the case, then I can say that for any of the supplier, for a supplier, and the D, which is the department ID, okay, the department purchase supplier, it has to be just one part. So it means that department can purchase part from supplier ID. Sorry, from a supplier. All right. So supplier, department, then you have this part ID, right? Now, so from here, I can see that uh, JP determines C comes from there. All right. And I have this C determines everything in the table here. So from here, I can actually imply that JP also determines the rest. Can you see that? What rule is this? Transitivity, right? If you get learn from the axiom Armstrong's axiom. So then I said, oh, yeah, all right, transitivity. And now you have SD implies P, sorry, SD determines P. It implies that if you have SDJ, also implies JP. What rule from Armstrong axiom is that? Exactly, augmentation. What about here? SDJ implies IP, sorry, JP. SDJ determines JP. JP determines the rest of the table, everything in the table. So it implies that SDJ determines the rest. What rule is this? In Armstrong's axiom, SDJ determines JP, JP determines everything in the table, and it implies that, yes, exactly, it's transitivity, right? And actually, there are many, many more if you use Armstrong axiom. So it keeps going. So it is like impossible to compute every F or every FD that comes from the original, just three here, right? Because we only have this one set because we know this from saying that the contract ID is a key. So then the key must determine everything in the table. And we have these two additional functional dependencies, and you compute like everything in the world there. So it could be very expensive because the size of the closure is actually exponential. So what do we do about it? Okay. We will make it a lot easier when we can compute what we call an X closure or attribute closure. So now, instead of compute all the F closure, but you have to understand what the F closures are, then now we use X closure or attribute closure here instead. All right. Uh, Now, this is a much more efficient way, and it is a possible way to check all the dependencies to see whether or not the data in the table dependent on each other. Now, instead of doing all the F closure, we'll do the X closure. How? We will do whether the X closure is in the Y. Let's see what do I mean by that. I'm gonna say like does F, I said I have a set of F. A determines B, B determines C. By the way, I said determines and I mean it functionally determines, right? So I just leave the functionally and call it determines. So A determines B, B determines C, C D determines E. Okay. Does it imply that A determines E? So what we do instead of the computing every F closure, what we do is just just want to check if E is in A, and that's it. All right. Now, how are we going to do it? Let's see how we do it. Let's say that we have A and B determine C here. You can see that if you have the same A, which is that X and X here, alpha and alpha here, you get the same C, right? And here you see you have Y and beta here. You have Y and beta here. You get the same C as well. So probably if you have only these data, you may be able to infer that maybe AB determines C. But if you have many, many more, it may not be true. So let's say that this is the case, then you can say that, well, AB may determine C. So yeah, basically we can say that, yep, we have the AB. And if you have the same AB again, it should have the same C. So now let's say that if I have the next tuple, I said X and beta, what would C be? X and beta. It must be 5, right? Because this X and beta, you already 5 in there. Exactly, right? So if I have Y and alpha, what happened? Can you determine C there? You don't know yet, right? Because you don't have the example, you don't have the same A and B to determine C. All right. So maybe you don't have enough information there. But basically, if you have X and alpha, C could be anything. But if you have the same X and alpha again, C would have to follow what X and alpha did before it. Okay? Now, uh, we'll go through how to determine X closure again. I mean, we'll follow that. So in order to do that, we have to come back and talk about prime and non-prime. I'm not sure if I talked about it before, but let's assume that this is a key, right? So now an attribute is a prime if it is part of any candidate key. So we have a table, we have key, and we have all the attribute, and we say that some of the attribute may be key, some of that attribute may not be key, right? Then we'll call them a prime attribute if it is a key or any part of the key. Okay, but I say candidate key because can be many, many keys, right? I'll call it candidate key for now. And then I'll give you the example. So I said the attribute is non-prime if it does not belong to the candidate key. So I have an example here. I have a table or a relation called car. And for car, I have city and plate number as key and tonnage, make, model, and year as their attributes that I did not underline. So for this example below, for car relation, what are the prime attributes? How many attributes are prime attributes? Just two, right? Because the description say that prime attribute is any attribute that is part of the candidate key. So candidate key that I underline are city and plate number. So it means that city and plate number are prime attributes. And how many non-prime attributes are there? The rest of them, right? Yep. So the rest, the four of them are non-prime attribute. And that's basically it. Now, just prime and non-prime. So when they are prime attributes, if they are part of the keys, and if they have nothing to do with the key, they are non-prime attributes. All right. So these are the uh, definition that we'll use. All right. Now, in order to determine X closure, we'll do this. I have a table here. And for this table, I will indicate left, middle, and right. All right. Okay. Now, please follow me because if you can follow me, it'll be very easy. All right. Now, I have the example here. A relation R has attribute A, B, and C. And I have a set of functional dependency with two functional dependency. A determines B and B determines C. What I will do is that I will lay down each of the attribute in this left, middle, and right table here to see that, for any dependencies, check the functional dependencies. I say that, well, is A is on the left, right, or middle of the arrow, right? And we have arrow in the middle here. So I say A determines B. So if A is always, always, always on the left, then we write down A here in the left. Now, let's take a look at C. Since C only appears on the right of the arrow, so we can write down C here. And now B is on the right in this first functional dependency, but B is on the left in the second functional dependency. So we say that B is in the middle. You still follow me, right? Now, so these left, middle, and right is very easy. But what does it mean? If it is always on the left, it must be part of the key, right? By itself, it may be just the key or part of the key because it's on the left. On the left, it means that this particular attribute actually can determine something in the table. So it must be part of the key. Now, if it's always on the right, it must not be any part of the key because it is determined by something else and it cannot determine anyone. So it must not be any part of the key. But now, one in the middle may or may not be part of the key. All right. So now what we'll do is that we will compute the attribute closure or X closure one by one, starting from the left one. Now we start from the left one, which is X closure. X closure here is an A closure. So we say A closure here. So we say A determines B, and we see that B determines C. So we can use the axiom, uh, oops. We can use the Armstrong axiom rules. And then, so what is I want to do this. Okay. So what is a closure? So when we say what a closure is, we know that A itself determines itself, right? And then we know that A determines B here. So we have B here, right? Also determines B. And we see that B determines C, so we can add it again, right? It's transitivity rules. So now we can say that, A uh A closure is actually can determine A, B, and C. So now, because we only have A, B, and C in this table, it means that A by itself can determine everything in the table. So yes, we can see that A is key. Did you get that? Or you want me to do it again? Again? It's fine. Do it again. All right. Okay. Uh, how do I make this one bigger? Oh, size. Okay. We want to compute. This one is so big. Wait. We want to compute the closure, right? No. Oh, this is difficult. How come? Ah, why can I not? Okay, what's happening now? I don't know why. Anyway, what we want to do is we want to compute closure. So after we do the table, then we'll start from the left one because we know that the on the left side it must determine something, so it must be part of the key. But we want to know whether or not it by itself, just the A, can determine everything in the table. So now we take a look at A first, and from these functional dependencies, we know that A determines B, and then B determines C. So we know that A closure actually determines A itself, determines B, B determines C. So A determines itself, it's like the given, right? Because it's on the left side. And then when I add A determines B, because it comes from the functional dependency that is given. Now, B determines C is the transitivity rules. So we know that A closure is can actually determines A, B, and C. You get it? All right. Okay. Now, so what it means when I say that A closure can determine A, B, and C, it means that just A by itself can determine everything in the table. So it means that A is a key. Okay. Now, let me ask you, can B be a key? Hmm. How? Hmm. Okay, so do we need to compute just B closure? If I compute B closure, what is B closure? So for B closure, let me do it here. Hmm. I don't know why I cannot use this. Uh, okay. Oh, I don't know why I cannot use this. I can wait. Should I compute B closure? Let's try. What would B closure be? If we take a look at B, then we know that B should determine itself, right? Can it determine itself? And but B, we know that B determines C, and that's it, right? How do I know this? Because the functional dependencies say so. So B cannot determines A, so it means that B cannot be a key. All right? Okay. Do we need to compute C at all? Okay. Anything on the right, in the right box here cannot be a key, right? Because it's always on the right of the functional dependency. So it can never be part of the key. So you never have to compute the closure for any attribute in the right box. All right? Okay. Now, but I did compute something in the middle box because it may or may not be part of the key. However, since A is already part of the key, what happen if I can I use A B closure as key? Should I compute A B closure? You can compute it, but it's not necessary. Why? Because if A is already a key, it's minimal, right? Because it can determine everything in the table. If you add B, if you add B, although AB can determine everything in the table, but it's not minimal, so it's not necessary to be computed, right? So since I already have A as key, it means that A is a prime remember prime and non-prime attribute, right? So A is prime and B and C is non-prime, a non-prime. All right. Okay, let's take a look at the next one. Uh, oops. Okay. Okay, let's take a look at the next one. I have a relation R, which has four attributes A, B, C, and D. Now, I have a set of functional dependencies saying A, B determines C, C determines B, and C determines D. All right. Now, first thing first, you take a look at each attribute and say, wow, A is always on the left. We don't see anywhere else, right? What about B? Actually, I already gave you the answer here, right? So B can be in the left here, can be in the right here. So B would go in the middle box. What about C? C is on the left, on the right here, on the left here, and on the left here. Also goes to the middle box. D is only on the right, so D goes here. So what it means is that A can be part of the key, D cannot be part of the key. But we don't know about B and C. So now first, let's do A closure. So you always start from the left box. Start from the left box. So now compute A closure. What is A closure? What is the answer of A closure? Can someone help me? So from A closure, you know that A, B determines C. Well, A closure is by itself. You get an A for sure, right? And then what else? You get the B. Yep, because of the Armstrong axiom, right? So you have A, B. Do you get C? Because A and B determine C, right? Can you? Really? Ah, let's compute. Yep. Think about it and compute A closure, then compute A B closure, then compute A C closure and A B C closure. Do it step by step and give me the answer. Think about it a little bit. I actually have the answer out here. I was going to use PowerPoint, which I hide the answer in the first place, but then I tried to use PowerPoint online, but all the symbols are gone. So I had to use the PDF here. Anyway, let's do it again. What is A closure here? From A, do you get B? You let me do this text. For A, you get A for sure, right? But do you know B? You do not know B because it doesn't say that A determines B, right? So here you only get the A. But now, what about, so you know that A cannot be just the key by itself. Now, you have to compute the next step by taking the attribute from the medium box, right? The middle box. So now you compute A, B closure. So we said that, well, A, B closure has itself A, B. And then because A, B determines C, you get the C there. And then C also determines D, you get the C there as well. The D there as well. You get it? Okay, now But you don't know whether, so actually you can say that, well, if you combine A and B, it can actually determines everything in the table, so it can be the key. But now you cannot stop because you have another attribute in the middle box as well. You have the C. So let's compute AC to see whether it can determine everything. So for AC closure, you have A. Do you have C? Of course. If you have AC, can you tell B? Because C can tell B, B can tell D, right? Oops, sorry. Then you have everything as well, right? So now, because of that, AC can also determines everything in the table. Now, do I have to compute A, B, and C closure? Because Ah, because it's not going to be minimal. Because you can say that AB or AC can be the key, right? Because it determines everything in the table. So if you add C, if you add another thing, if A, B, C, it's not necessary because just the two would be minimal key already. So now you know that A, B, and C would be prime attribute because key can be AB or AC. So ABC would be prime attribute, while the D is a non-prime attribute in this case. All right. Now let's take a look at the third one. Oops. Okay. Let's take a look at the third example here. I have A determines B, B determines C, and C determines A. So you can see that there is nothing on the left box because A is on the left here and on the right here, B on the right here and on the left here, and C on the right and on the left as well. So everything is in the middle box. So now we have to compute everything in the middle box because nothing is on the left, right? So let's start with A closure. What is A closure? What is A closure? So A determines B, B determines C, C also determines A. So it determines everything, right? Now, let's try the next one. What about B closure? So it's a B determines C, C determines A determines B. So it has everything as well. And then what about C closure? C closure says C determines A determines B, B determines C. So it means that either A, B, or C can be a key. So in this case, key can be either one, and all of them are prime attributes, and there is no non-prime attributes. All right? Okay. Oops. Be clear. Annotation. Okay. Another example here, just to make sure that you get it. We have A, B, C, D, E, and we have set of functional dependency where I say A determines D, D determines B, B determines C, and E determines B. So let's start with uh, putting them in the box, right? So A is actually on the left here, just on the left. What about D? D is in the middle because it's on the right here, on the left here. What about B? B is on the right here, on the left here, also goes to the middle box. We have C in the left, in the right, just in the right, and we have the E on the left only. So now we have AE in the left box, BG in the middle box, and C in the right box. Now, what we'll do is that we'll take everything in the left box and see if it determines everything. So we compute AE closure. What would be the answer? So you can see here that A determines D, right? And we see we have AE. So E determines B, and B determines C here. A, D, B, C. What is left? Oh, E by itself, right? Because we have AE there. A, B, C, D, E. So now we have everything. Sorry? Oops. Sorry. Okay. Oh, wait. A, B, C, D, E. How do I fix this? Let me clear. Okay. Actually, you know that it determines everything there. All right. So it means that AE would be key. So prime attribute would be A and E, and the rest would be non-prime. So basically, what I have shown you is that when you look at the table and you have the functional dependency, you can always compute the key. You don't actually have to see the sample of the data in order to determine the key, but you can always compute the key from its functional dependency this way. All right. Now, uh, take a look at the next one. So we talk about determines all these keys. But now let's see that if we have the example here. We have a table called employee, which is in the first normal form. We'll talk about normal form a little bit later, but let's take a look at this table called employee. We have employee number, name, department number, department name, and skills, right? And now we have the functional dependency. Okay, we said that name, department number, and department name are functionally dependent on employee number. Well, how do you know that? Because if you have the same employee number here, let's say employee number 1, you always get the same name. You get the same department number. You get the same department name, but you don't get the same skills, right? So what does this mean? If you have the example, the data example, you can see from here that the employee number actually functionally determines name, department number, and department name, but not skills. Not skills. All right. Now, okay. So what do we do from here? If you know that employee number determines the rest, but skills is not dependent on employee number, what to do next? How do you identify the key from here? You understand my question? I'm saying that employee number determines name, department number, and department name, but not skills. But how do we make it? How do we make the whole table have the key? So what happened is that if it does not determine skills, we need to combine whatever it does not have the key there. I mean, it's not dependent on it to become a composite key. Employee number and skills will be composite key to make key for this table. So what I mean is that uh here I will have to underline employee number and skills here as composite key. All right. Now let's take a look into more detail so you understand it a little better. Let's see this example. I have a table called movie, and movie has title, year, length, film type, studio name, and star name. Now, from here, you have the data. You can see that if you have the same title, you see the same year, same length, same film type, same studio name, but not the same star name. All right. Again, if you have the same title, Wayne's World here, you have the same year, length, film type, studio name, again, not star's name. So from here, you can assert that title and year determines length. It also determines film type. It also determines studio name, but it does not determine star name. So these are the functional dependencies that you learn if you see the data, right? If you see the data, you can write out these functional dependencies given the data that you see. All right. Now, another example. I have hourly employees here in the table, and it has social security number. It has name, lot, rating, hourly wages, hours worked. The orange letter here are what I'm gonna write down, so it's shorter. So denote this relation using the orange color letters there. So this is actually the set of attributes from these 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 of the attribute SNLRWH. Now, we can also refer to it as hourly M's table. So for these, I have SSN underlines. So it means that SSN is a key of the table because SSN can determine name. So if I have the same SSN, it must be the same name, same lot, same rating, same hourly wages, and same hours worked. But now I want to assert more FD. So I'm saying that I want to say that the rating could determines hourly wages. So I mean, if given every R, it must be the same W. For example, like rating A1, you will get like this wage hourly, right? And if rating is different, you get different wage. If I do that, I can, let's see that the table here came from this one. You have these 6 attribute for hourly M's here. And if I have the table here with the instances in there, you will see the data or the tuples in the database. Let's say that for these, I do not assume any functional dependency. Also, there is no legal here, no instance, any instance is legal. So you can have like more tuples here. And I would assume no redundancy. So what I mean here is that for this table, that I have no functional dependency. If I am going to add one more tuple, let's say that I am going to add, annotate here, the next tuple, I can insert like, oh, sorry, anyone, right? And I said name is blah, 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 blah. Lot is anything. You can just assert anything. And then I can say as 5, and then W could be 20, and hours could be 2. If I assume no functional dependency, I can just add anything because there is nothing related to each other, right? This is just like no functional dependencies, right? So it means that if you take a look at this, although the data indicates that, with the same R, you should get the same W, right? For 8, you get W as 10. For 5, you get W as 7. But if I assume no dependency, I can actually add 5 with different W. This is no functional dependencies. But now, let's try again. Take a look at when we have functional dependencies in place on the next slide. I'm saying that if I know that SSN is the key, so I know that S determines all 6 attributes in the table, all right? Now, I added another functional dependency saying that R determines W. So now, if I add another tuple, okay, here. Okay, let me see that. If I add another tuple, I say 1, 2, 3, 2, 2, 3, 6, 6, 6. What must be in the name? It has to be this, right? Because now I know that as the same SSN, I must get the same N, L, R, W, and H, right? So I will get exactly the same, the first tuple there. I have to repeat that. But now, if I have the next person, I say 3, 6, 6, 7. It can be someone else, right? Now, it can be someone else. So the lot can be anything. Lot can be anything. And then if I have R as 5, what would be W? Ah, Exactly. W must be 7. Why? Because I say R determines W, right? So for the same R, I must get the same W. So if R is 5, then I get 7 there. What if R is 8? W must be 10. What if R is 4? We have no value. So can be anything from there, right? Exactly. So ours could be anything because it doesn't have any dependencies. So this is what it means by dependencies, right? Functional dependencies. Good. Okay. Let's take a look at the next one. You can see that if we have the table like this, I add more R, you get the same W. So the problem with this is that it can cause some anomaly in the table. So let's take a look at the first anomaly called update anomaly. What if we change the W in the first tuple? What if we change it? W here. If I change W here to 9, let's say, what would happen? It would be wrong, right? Because the rest would be different because I said R would determine W. So the rest of the R must be 9, but is not the case because you only changed this. So this is called an update anomaly. So it caused the table to be corrupted because R determines W will not hold anymore. Now, what about insertion anomaly? What if we want to insert an employee and don't know the hourly wage for this rating? So if I add another person, say R is 9, then we don't know what W could be. So that is called an insertion anomaly. What about deletion anomaly? It would happen when if you delete all employees with rating 5, like you delete this person, then you want to add another person. You already lost the information about R being 5, then W is 7, right? You lost that information. So this is called deletion anomaly, right? So how are we going to fix it? We are going to decompose the table, all right? So again, I just want to stress that there would be 3 different anomalies: update anomaly, insertion anomaly, and deletion anomaly. Okay, let's take a look at how we are going to decompose it. All right. To decompose it, I decompose that big table into 2 smaller tables called hourly Ms2 and wages. So basically, the R determines W are separated such that, let me show you, such that R determines W is in a table by itself. Okay? But you cannot eliminate R altogether from this table. But W is gone because R and W is in the table, is in another table. So in this table, you have S, N, L, R, and H. Now, if you add another person here, blah, 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 and you have the same R. Let's say that R is 5. You don't have to add W because W would be associated from this table. Sometimes we call it a lookup table. All right. So from this lookup table, you will know that every time that it is 5, then you will get a 7 for W. Though these lookup table can be a lot longer. Let's say like if this is 1, it can be 11. If it's 2, it's 20. This is like example. If it's 3, it's something else. If it's 4, it's something else, blah, 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 blah. So then you can take a look at these table and nothing would be gone because let's take a look that let's try the problem of deletion anomaly that we saw on the previous slide. I said that if I delete these 2, right? Anyone with R being 5, then I would not lose the information of 5 is equal to 7 in W because it's already in the lookup table. You know what I mean, right? Or you want me to say it again? It's okay now, right? Still okay? right? Now, so what we do is that if there are some redundancies, we call it redundancies. For example, how do you know if it's redundant? It came from the functional dependency. So functional dependencies say that, well, in this table, there might be some redundancy. So decompose them. Decompose them. So we decompose them in two different smaller tables. All right. Now, how do we know? How much do we need to decompose into smaller table? Do we need to decompose them again? Now, the reason and the steps to decompose any table would be called normalization. All right. And then we will decompose them with normalization process into different normal forms. So these are related from, the relationships from functional dependency, the F closure, the X closure, the keys, the prime, non-prime, and now the normalization process. All right. Okay. Before we go into the normalization, let me go back to the null values again. So a lot of time when table have null values, it will be wasted also, and it's so we basically so the relation should be designed such that their tuples will have as few null values as possible. We don't want the table with a lot of null values. It doesn't make sense, right? So the attribute that are null frequently could be placed in a separate relations with a primary key. That is one of the suggestions. And null value can actually address insertion and deletion anomaly. So that's why we want to reduce the null as much as we can. All right. Now, the normalization is actually, again, the process of decomposing the bad relations into smaller tables, and hopefully they should be better relations. All right. But when I talk about being better relations, it doesn't mean that it is most efficient. Okay. It can be better designed, but less efficient, but we can fix that later on. So for the step of normalization, we want them to have less or least redundancy as possible. All right. So the normal form is we will use the key and functional dependency to determine the form. And again, we'll cover just first, second, third, and BCNF. But only second, third, and BCNF are based on key and FD. The first normal form doesn't have to depend on key and FD. It's something else. All right. So uh, before we go into that, another thing to uh, note is that there are two very important properties when you do the decomposition. The first one is called lossless join decomposition, and this is mandatory. I have like 3 asterisks there to say that it is mandatory. What it means is that you are going to decompose a table, right? So from bigger table, you have smaller tables. And now, when you want to use them again, you may be able to join them back. So whenever you join them back, these properties say that whenever you join the tables back, you should not get the meaningless data when joining back. So what it means is that it should be lossless join. They call it lossless join. So you do not lose any data, or you do not have any additive data, which is not which may make it wrong. So basically, it's called the lossless join, or sometimes it's called non-loss or non-additive join, because you should not lose data and you should not add data that is incorrect into the table. So you have to make sure that the once you decompose the table already, make sure that those smaller tables, when joined back, they will arrive at the original tables. All right. When you arrive or the result is the original table, it means that you do not lose any tuples and you do not have additional tuples. You get it? So this property is a must. It is mandatory. Otherwise, the table can be wrong. Now, there is another property, but I only have one asterisk saying nice to have. So this nice to have say that it is called the dependency preserving decomposition. It means that when you decompose the table into smaller tables, all the functional dependencies must remain the same. You must not lose any functional dependency. However, because I said nice to have, so it is good to have, it is good not to lose any functional dependency, but it can. So if it loses some functional dependencies, it's okay. Okay. It doesn't really matter, but it's nice to have. All right. But the first one, again, the lossless join decomposition says that once you decompose them already, make sure that if you join them back again, you do not have additional data and you do not lose any data. All right. Here, let's take a look at, if you remember from last time when we do the join function, okay, the join command, which actually comes from the times, right? And then you select. Okay, now let's take a look at decomposition. When you do the decompose here, I just want to tell you that from the last time you do, whenever we do join, there are two different steps, right? You times them and then you select them. And then for the decomposition, again, you have to put them back together. You have to make sure that when you put them back together, they're still the same, right? So let's take a look at the decomposition step first. Let's say if you are decomposing these table, we have R here, table R here. Table asset, we have B name, B city, we have assets, C name, L number, and amount. If I want to decompose R into R1 and R2, so I said that R1 has B name, B city, assets, and C name. And in R2, I have C name, L number, and amount. So let me annotate here. B name goes here, B city goes here, assets go here, C name goes here. C name also goes here, L number here, and amount here. All right. So I decompose them into two smaller tables. When you compose two smaller tables, you need to make sure that R1 and R2 union will have to be the same as the original one. All right. This is a union property. But now you look at the instance, you can see that if I decompose it that way, I have C name in two tables, then what happened is that I am going to have four tuples on each of the smaller tables here, right? So this is one way of the decomposition. But now you have to check whether when you join them back, they are still the same. So it's the same meaning that you have this right data. Let's see what happened that. Okay. Now, the one that I show you is actually a bad decomposition, and let's see why. Okay, I have this table, B names, B city, asset, C name, L number, and amount, and I decompose it into two tables here. And then when I join them back, I have, you know that to join back, you have C name and C name here, right? So you matched C name, right? So C name comes here. So when you join them back, you get all these six lines there. When you join them back, so you have like downtown BKLN, downtown BKLN and Jones, downtown BKLN and Jones, but you have this different L number. So when you join them back, you have these two extra tuples. That is wrong because the original one already only have four tuples, right? But when you join them, what happened is that there are six lines or six tuples, and you have these two additional tuples. So it makes the original, it's not equal to the original table. So this is a problem of the lossy join. This is called lossy join. It's not lossless join. All right. It's actually not lossy because you didn't lose information. It's like additive, right? So it still is called lossy because it's not the right one. Okay, so this is a very bad example of joining where what I'm saying is that you should not join them or you should not decompose them this way, right? Now, How are we going to decompose them? There are some rules to decompose it in the right way. So let's take a look at these decomposition. Okay. Is it losses or lossy? I have B name, asset, C name, and L number. And here I have L number, BCD, and amount. So you can see that in the last example, I joined them with C name, but here I join them with L number. So if I no, I decompose it, having L number on both sides, on both of the smaller tables. But now, if I'm joining them back, because they are joined with L number, how many tuples will be in the result if I join this table back together? So you join them and then you match uh, the L number together, right? Now, would it be lossy or lossless? Lossy or lossless? It'll take a while because you will have to uh, can you say again? Uh, so actually, if you join them back, you get these. You have four tuples here. You have three tuples there. So you times them, right? Now you should have like 12, but then you have to match L number, L number, L number. You only select all the same L number. So actually, this is a good example of decomposition. So basically, I want to tell you that the good way to decompose them, the good way to decompose them, you have to have the key. So if L number is one of the key, it's a key on one of the side of the smaller tables, then it will make sure that the decomposition will be lossless. All right. So this actually is a lossless one. If you compute, you will have the same four tuples as original one. Right. So basically, because I choose to decompose using the key, so that would be something that you have to do when you decompose. You have to use a key on one. There must be a key on one side. So when you join them back, it would be lossless. Okay. So, to sum up about lossless joint decomposition, so the decomposition of R, like you have R1 union R2, the losses will occur if and only if R1 union R2 determines R2, or R1 union R2, intersect R1 intersect R2 determines R1, or R1 intersects R2 determines R2. So basically, it's a key, right? One side is a key. Or I'm saying that the intersecting attribute must be a super key for one of the resulting smaller relations, right? So in the previous example, the L number is the key or super key. Let's take a look at another example before we take a break. Suppose that we decompose a schema R. We have A, B, C, D, E, and then we compose it into R1 and R2, where I have A, B, C, and A, D, E. Okay. All right. What I'm going to do is that show that this composition is a lossless joint decomposition if the following set of F of functional dependencies holds. All right. How can you tell whether it is a good one if it is a lossless joint there? So basically, if I have F1, I say the functional dependency say A determines B, C D determines E, B determines D, and E determines A. What happened is that a decomposition of R1 and R2 is a lossless joint if R1 intersects R2 determines R1, or R1 intersects R2 determines R2, right? So let's say that if R1 intersects R2 is what? What do you get from R1 intersects R2? You get the A, right? The intersection between these two, R1 and R2 is the A, right? Now, because R1 and R2, does it determine R? So let's say if A determines the rest in R1 and A also determines the rest in R2 here. Since R1 and R2 is equal to A and A is a candidate key of R1, therefore R1 intersects R2 also determines R1. So we know that it's a key. All right. How do we know that it's a key? Because here A determines B, C, right? So in R1, because we know that A determines B and C, it means that A is a key, right? Mm. Now, C and D determines E, doesn't say anything about key. We know that B determines D. B determines D is not a key, but E determines A. In the second one, E determines A. So E may be part of the key because E determines A, but who determines D? Said B determines D. So it does not say that E determines the rest, right? But at least we know that A is determining B and C in R1. Okay. So A is a candidate key of R1. Okay. Therefore, R1 and R intersects R2 would determine R1. Okay, because of this rule here. Now, let's take a break. Oh, I have another one here. Oh, yeah, let's take a break and come back later. It's 10:30. Let's take 10 minutes break. Okay, let's get started. Uh, so I can finish this in time. I have 51 slides, so 20 more. So let's take a look at another example of lossy joint decomposition, which is another example of the lossy, which is not lossless. So lossless versus lossy. Um, so it means that lossy is a bad one, right? So let's see this example. I have two tables here. Okay, I have R with, one table here with two attribute A and B. All right. Now I decompose it into two, R1 and R2. So R1 only have A and RB only have B. R2 only have B. So what happened is that there is only one attribute on each side. So, from here, alpha is 1, alpha 2, beta 1. I have alpha and beta here because alpha has duplicate and I have 1 and 2 here. So when you join them back, you will get these four lines, right? So basically this is a lossy join because you have additive uh, attribute there, additional attribute there, which is wrong because it's not in the first or it's not in the original table. But what happened is that because you have A and B here, you do not have any key to join them back. So that is one of the problems that arises. You can see clearly from here. Now, there is one more slide before I go into normal form. All right. So this is another thing I want to discuss about the dependency preservation. And let's take a look at the example. Okay. I have table R, which comprises city, street number, and zip code. And I have two FD. The first FD say that city and street number determine zip code, and zip code determines city. So I decompose it into street number and zip code, street number and zip code 1. And then I have city and zip code. Is it a good decomposition? Is it a good decomposition? Is it good? It is good because I use the key, right? I have zip code here. So zip code actually determines city. So I have the zip code on both sides. So this is a lossless decomposition. But this is the first rule. Remember, I have two properties, right? The first one that must abide by is that when you join them back, it must be losses, no extra tuples, no loss tuple. So that is fine. But now the second property says that we should preserve dependencies as much as possible. So basically, we want to know if the smaller table, when I already decompose it to R1 and R2, I want to know whether the dependencies is preserved. So let's see, is the, let's take a look at the, whether zip code determines city is still hold in both, on both sides. So zip code and city is here, but zip code is city in not in the street number. So it means that maybe just one of the table, which is R2, actually preserve the dependency, but not the other one. So this is how to check the dependency. So you have, when you check the dependency, another way to check the dependency is actually you have to join the table back and to check whether the dependency is still there. So this is very expensive, very costly. So usually we don't do that. All right. We don't need to check every table to see whether the dependency preservations are all there. Okay. So let me stress again. Let me go back to the other slide when I say that there are two properties here. Just want to stress again and again that losses must, this is a must, it's mandatory. You must make sure that once you decompose a table, and if you decompose them and put them back, you must not have additional data. You must not lose any data. So that is called the lossless join decomposition, and you must do that. All right. In order to decompose and make sure that it's lossless join, you should decompose having key on one side, right? At least on the one side. And then, or having key being decomposed into two sides. But now, for dependency preservation or dependency preserving decomposition, it is very difficult to check. So you can disregard it. All right. But it is one of the property that is good to have, but it is almost impossible to check. So we can disregard it. All right. Now, we have done this. So now we are here at the first normal form. So we have first, second, third, and B and F. We have four normal forms to cover. And the first one says that in the first normal form, it disallows composition attributes, multi-valued attributes, and nested relation. So attribute, it means that attribute whose values is for an individual tuple are non-atomic, we do not allow anything. So we only allow single atomic value. What does it mean by that? Let's take a look, right? If I have a table here, department, and I have department name, department number, department manager SSN, and department locations there. And if you remember from, well, I think last 2 weeks, last 3 weeks, uh, we say that the D location are multi-valued. What it means is that for one location, for one of the department, there can be many locations, right? So department can have many locations. So if you have instance, might look like this. We have a department name research, D number D5, D manager is assigned as this. And then for D location, we said that department number 5 may be located in Bel Air, in Sugar Land, or in Houston. But for department number 4, it's only in Stafford, and department number 1 is only in Houston. So now you can see that department number 5 has many locations. This is not atomic. So when I say atomic, you could only have one data for that particular value. So D location can only have one data. So how are we going to fix it? We are going to fix it such that it is an atomic value in each of the cell. So basically, here we have uh, D name, D number, D manager assistant, and we have D locations. The difference is that now D location can only have one atomic value, but you have to expand the table or the tuple such that you have like research, 5, same D manager assistant, and then you have D location, different D location on each of the tuple. But in order to do this, you have to assign D number and D location as key, right? Otherwise, if you have the same D number, okay, let's take a look at this. If the location is not part of the key, what would happen? You cannot have the same D number, right? So now if you assign D number and D location as key, composite key, then you have 5 and Bel Air, 5 and Sugarland, 5 and Houston, which is okay now, right? Now, can I have the next line as 5 and Bel Air? Cannot, right? Because it's a key, so you cannot have duplicate. All right, it's very good. Now, so right now, it is in the first normal form here. It's in the first normal form because everything is already atomic. This one is non-atomic because you have 3 values for the D locations, but here you have atomic. So now it is in first normal form. All right. Now, so for the first normal form, we say that remove duplicates and place in a separate relation and expand the key. All right. So that is what we can do is that this is another way to do it. So if I did, let me stress it again. Here, what I did is that I have the location and assign the location with the D number to become key, right? So then that would hold. Another way to do it is that you remove the duplicate and place in a separate relation and expand the key. So basically from last one, I have decomposed them into department and department locations. So for the department, I have D name, D number, and D manager assistant. And then for the department location, I have D number and then D location. So now I have 2 tables, right? This is a second way to fix the non-atomic problem. All right. The second way I said, well, let's decompose them into 2 tables. So for the first table, first smaller table, I have D name, D number, and D manager assistant. Smaller one, I still have D number, and then now I assign D location and D number as composite key. Okay? Now, another way to fix it is that if I know that there must not be more than 3 locations, then I can fix it such that I have department table with the name, the number, the managers then, and instead of having these 2 smaller tables, I can say the location 1, 2, and 3. So these would also fix the non-atomic problem, but there are some drawbacks here. So, for example, the number 5 have 3 locations, but all the rest only have 1 location. So then the D location in number 1, you have some value, but in D location number 2 and number 3, it would be null, right? So you introduce null in many places there. So it's not really bad, but it could have some storage waste, right? Let's see. Now, let's take a look at another one. I have table employee here where I have employee number, employee name, department number, department name, and skills. Okay. You can see that for skills, there are multi-value, right? So it's not atomic again. So to fix it, I use the first example, the algorithm for the first example where I said that, well, let's make M number and skills become composite key and make it atomic. So I have C, Perl, Java, Linux, and the rest lined up in different tuples. So I have additional tuples for each of the employee skills, right? Right. So this is not uh, complicated. But let's see. Let's take a look at another example here. I have SSN name, okay, for M project. And then I have a composite attribute called project with P number and hours. And if you take a look at the instance, you can see that for SSN 1, 2, 3, 4, 5, 6, 7, 8, 9 with P number, he has two P number. He has two projects. And for each of the project, the hours that he worked for the project is different. So these are not atomic again, because for hours and P number, you have multiple values. So in that case, we need to decompose them in order to make it, we can decompose or we can assign the composite keys in order to make them atomic. So everything must be atomic to become the first normal form. All right. Okay. So this way, what I did is that I have SSN and SSN and E name in one of the smaller table. And then I put SSNP number, SSNP number in another table to form a decomposition and then put hours in there. All right. Okay. So now everything would be atomic. So everything's fine. It would be in first normal form. So first normal form, the only thing that first normal form asks is that all the data in the table must be atomic. All right. Okay, now let's go to the second normal form. Second normal form say that a relation is in the second normal form if it must be in the first normal form first, and then this is important, every non-prime. Now, that's why I have to introduce prime non-prime beforehand. Every non-prime or non-key attribute depends on the whole candidate key. There would be no partial dependency or part of the composite key. What does that mean? Okay. It say for prime attribute, okay, again, it's the attribute that it's a member of the primary key. And the full functional dependency means that if you have Y determines Z, you cannot remove any of the part of the key for the dependency to be held. All right. Let's take a look at the example. If I have Social Security number and P number determines hours. This is full dependency since you cannot remove anything and it still holds. So SSN alone cannot tell hours or P number alone cannot determine hours. So you must have SSN and P number to determine hours. All right. Now, if I have SSN and P number determines employee name, this is not a full functional dependency because actually only SSN can tell E name, right? You don't need P number to tell E name. So this is not a full functional dependency because this attribute E name only depend on part of the key, not the whole key. All right. Now, so far good. Let's take a look at this. I have mproj relation there. I have SSN, P number, hours, E name, P name, and P location. And functional dependencies, number one, say that SSN and P number determines hours. Okay. Second, functional dependency say that SSN itself, just the SSN determines on E name. Okay. So FD number 3 says that P number determines P name and P location. All right. Now, is it in first normal form? To check whether it is in second normal form, it first must be in first normal form first, right? So let's assume that everything is atomic, right? No multi-value, no nested, no combination or anything. So it is in first normal form. But is it in the second normal form? Okay. We say that it would be in a second normal form if all the non-prime attribute depend on the whole key. All right. So let's take a look. What is non-prime attribute? So this is non-prime, 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 and these are prime because SSN and P number has underlined underneath it, right? So they are keys. Now, so we say that non-prime, let's take a look at hours. So hours depend on what? Depend on the whole key. It does, right? Because hours depends on P number and SSN given this FD number 1. All right. Now, the problem is this FD number 2, because FD number 2 says that e-name actually is determined by just SSN, right? Now, this is not the whole key because SSN is only part of the key. So this FD2 does not pass second normal form. Okay? Same as FD3. FD3 say that P name and P location depends on P number alone, not depend on SSN. So it's only part of the key, not the whole key again. So FD3 did not pass second normal form requirement. So we have to denormalize them. So we no, sorry, not denormalize, decompose them. So how would I decompose them? I decompose them into 3 smaller tables, all right, in 3 smaller tables, given the functional dependency. So the way that you decompose it, take a look at the functional dependencies because it implies the keys, right? So for the first decomposition, I said EP or MParch number 1, I take the first functional dependency SSN P number determines hours. And the second one I have SSN just determines E name. And then EP3 would come from FD3 where we say P number determines P name and P location. All right. Now, check it again, whether all the decomposition tables are in the second normal form. So let's see. Ours is non-prime and it depends on the whole key, which is SSN and P number. So that's good, right? This one E name depends on SSN and SSN is the only key. So it's good. This one P location and P name depends on P number. So P number is the only key. So it's good. All right. So yep, this is the whole thing about second normal form. All right. Now, more example. If I have M number determines name, department number, and department name, but not skills. You remember that, right? Now, I can decompose them into 2 tables called employee and skills, where in employee, I would say that it would be in second normal form if I have these because I decompose them into 2 tables. So now I have M number, name, department number, and department name. And then I separate M number and skills into another table. And I assign both M number and skills to become key so that now skills and M number, you can have like a set of M number and skills there in just that table. You can see that these 2 separate tables would have less redundancy, right? Because here, see, you have these duplicates, right? A lot of duplications. So then if you have more skills, you have to duplicate M number, you have to duplicate all 4. But with these, you would take a lot less space because it would be saved. But not only that, for example, if you delete one of the thing, it may corrupt the table if you do not delete it or add something, or it can have anomalies occur in the table if you did not do it with care. So basically, if you decompose them correctly into the second normal form, it should save you space and it should reduce anomalies that could happen along the way as well. All right. Now, third normal form. Third normal form is very important because most of the time when you go into the company, you will hear that, make sure the table is in third normal form. This is very standard. So the standard practice, in the real world is actually this third normal form. So what does it say? It says that a relation would be in third normal form if it is in second normal form and has no transitive dependency. All right. So the transitive dependency is on the non-prime attribute on a key So let's see what it does. So let's say again, the transitive functional dependency says transitive says that when you have X determines Z, actually, if it comes from two functional dependency where X determine Y and Y determines Z, and you transitively implies that X determines Z. This is a problem of transitive functional dependency that third normal form does not like, right? It does not allow you to have transitive functional dependencies in the relations. For example, I have SSN determines D manager SSN. It is transitive because actually SSN actually determines D number. So you know SSN, you know D number, right? Department number. And when you know department number, you know which department SSN it is. So that is a transitive because if you say SSN determine D manager SSN, it can actually cross from this to this, right? So that is the example of the transitive functional dependency that third normal form does not allow, right? So I have a note in here. I said that if X determine Y and Y determine Z, okay, and if X is a primary key, we consider this problem only if Y is not a candidate key, all right? For example here, I have a table called EMP, and I have SSN, employee, and salary. All right. So because uh, this is not a very good example of a table because if I have SSN, which is a key, but actually if you have employee number, it can be a key as well, right? Because it's unique. You have employee number. So it means that you have a candidate key. So if you have a candidate key in this case, you will not be worried about the transitive dependencies in this case, right? Okay. Take a look at this example. I have employee department table there, where I have SSN as key, and I have E name, B date, address, D number, D name, and D manager SSN. All right. FD1 says that SSN determines E name, B date, address, and D number. And then it says that D number determines D name and D manager SSN in FD2. Now, is it in second normal form? Let's assume it is in first because everything is atomic. Now, is it in second normal form? Second normal form says that everything must depend on just the key, right? But because we only have one key, so everything is in first normal form. Sorry, second normal form already. Now, it's not in third because if you take a look at FD2, all right, we took a look at SD2, you can see that D number determines D name and also determines D manager SSN. It is transitive because let's say that D manager SSN actually depends on D number and D number depends on SSN. Let me draw the line here. D manager SSN depends on D number here and D number depends on SSN. So this is transitive because SSN determines D number determines manager SSN given the FD 1 and 2. So this way it does not fit the third normal form requirement. So we need to decompose them. So I decompose them into two tables using those transitive value, which is D number here. This is the problem of transitive, right? So when it is transitive, we use that transitive attribute and create a table, another table. So we decompose them into ED1 and ED2, where ED2 takes a D number, D name, and D manager SSN from FD2, and it will be eliminated from ED1. So we have these two tables, which is now does not have any transitive dependencies anymore. Okay? Okay, there is also another alternative way to take a look and to compute whether the table is in a third normal form. You have these alternative way here. There are two conditions. First of all, we need to talk about super key of the relation. It says that super key of a relation schema R is a set of attribute S of R that contains a key of R. So you remember super key, right? If you don't, I will remind you again. Super key can be any combination of the attributes that can determine the rest, right? Now, I say that a relation schema R is in third normal form if whenever an FD, okay, functional dependency, say X determines A holds in R, then either X is a superkey of R or A is a prime attribute of R. So the way to check whether it is in third normal form, you can use either way. This is or. So if X is superkey of R, then it is in third normal form. Or if A is prime attribute of R, it's also in third normal form. However, there will be a next normal form called BCNF or Boyce-Codd normal form that does not allow B to happen. So third normal form allows A or B, but Boyce-Codd normal form only allows A. So let's take a look at how we use this. Okay. We have, oops, I think, did I forget to? Am I still recording? I'm recording, right? Okay. Okay. Now, let's take a look. We have this example where I have a table called lots, okay, a relation called lots. I have property ID, county name, lot number, area, price, and tax rate, right? And I have FD1. FD1 says that property ID determines county name, lot number, area, price, and tax rate. So basically from FD1, what is the key of this table given FD1? So it is easy, right? So from FD1, we see that property ID is a key because it determines everything in the table. Now, let's take a look at FD2. This is the special case. FD2 says that if we know county name and lot number, FD2 here, we can also determine the rest of the table. What does this mean? So this means that if you take county name and lot number, it could be a key, right? Because it determines every other attribute in the table. But you remember that you can have candidate key and you can choose just one to become primary key, right? And in this case, you actually have two set of keys. So this is one set of key and this is another set of key. So I call key one and key two. But you choose K1 or the property ID to become key for this particular one. Okay? Now, next FD says that county name can actually determine tax rate. So for example, you know that you live in a county called Wang Mai, and you know that the tax rate for Wang Mai is this percentage, and that's it, right? And now you also have FD4. You said that if you know the area, then you know the price. All right. Now we will check all normal forms. All right. So let's say for the A, it said the lots relation with its functional dependencies FD1 to FD4 that we just talked about. So now we want to decompose. So step B, we decompose into the second normal form relation, lots A and lots B. Okay. Okay. Remember what does second normal form say? Second normal form say that all the non-prime attribute has to depend on the whole key, cannot depend on just on partial key. All right. So let's take a look at FD number one. Sorry, on A. Clear all my drawings first. Okay. Non-prime attribute County name, lot area, price, and tax rate given FD1, it all depends on the key, which is called property ID. So this is good, right? Now, for FD2, you say county name and lot number actually determines the rest, which is still good. Now, for FD3, you said that county name determines tax rate. So it means that tax rate actually only depend on county name, but you remember that county name and lot number together form a candidate key, right? So this means that in FD3, what tax rate actually was determined by just county name would not pass second normal form, right? Because it only depends on the partial key. So we have to fix it. So for these, we take the lot number. Oh, sorry. We take the county name and tax rate and decompose it into a smaller table and maintain the rest. So we still have county name in here, but not tax rate because tax rate is removed and put it in the smaller tables there. Get it? All right. Okay. So that is already in second normal form. Now, for step C, we want to decompose into third normal form. All right. Now, let's check the FD again. From lots 1 here that we already decomposed, let's check whether we have problem of transitive dependency, where what that is the problem for third normal form, that it does not allow transitive dependency, right? So how do we know if there is a transitive dependencies? Because FD1 says that it determines everything. FD2 says that county name and lots determine everything. But FD4 here says that area determines price. You can see that, right? So price depends on area, but area depends on what? Depends on property ID, or actually it depends on both lots and county name. So this is a transitive dependencies, right? Transitive because price actually depends just on the area. Just on the area. So, but area actually depends on the key. So you cannot say that property, you can imply that property determines price, but actually it's a transitive dependency there, which third normal form does not allow. So we need to decompose them into these two smaller tables where we take the price and area here, the transitive set here, and the rest in the main one. Okay, so that would fix the transitive dependencies there. So now, if you take a look at what happened is that the lots actually in first normal form, and when you decompose it into lots 1 and lots 2, it's in second normal form. But you have to further decompose lots 1 into lots 1A and lots 1B in order to obtain third normal form there. Okay? Now, the last normal form is called Boycott normal form. For Boycott normal form, if you remember that there were two ways to determine whether the table is in third normal form. There were two ways, A and B, and I said that B is not allowed in the Boycott normal form. Here we were going to use that. So the relation schema is in Boycott normal form. If whenever FDX determines A holds in R, then X is a superkey of R. So the keyword is a superkey. All right, it's a superkey. All right. So for each normal form, you can see that it is stricter from one to another. Like Second normal form must be in first, third must be in second, and BCNF must be in third normal form first. So there may be some of the relations that is in third normal form but not in BCNF, but it is very rare. So if you go into a company as intern and you are working on databases and you want to find BCNF, it's actually very rare. Okay. But the goal is to have a BCNF. If the goal is to have a BCNF, let me show you how. Okay. Okay. Here. Okay. I have lots A here, if you remember, with FD1, FD2, lots 1A, which we already decomposed into a third normal form. But now we have an extra functional dependency saying that area actually determines county name. So basically, if I know that the area is in Wang Mai, I know county name is Pathumwan, something like that. All right. So in this case, we need to further normalize it into BCNF. Okay, this is the way to do it. I said that lots 1AX and lots 1AY. And the first one would only contain property ID, area, and lot. And then, according to FD5, we decompose area and county name because area determines county name. And then the rest would be in lots 1AX. Okay, this is the decomposition into X and Y. Okay. Now, when you check BCNF, I think I would show you this. I think this is the easiest way to determine or to recognize whether it has the problem of BCNF. When you have A and B determine C, you know that A and B should be the prime attribute, right? Like part of the key. But now, if you have the non-prime, which is a C, which actually determines prime, this is weird, right? Because you have the non-prime that actually determines back to the prime. This is when BCNF happens. So that's why I said it is a very rare case that you have the non-prime that actually determines back the prime attribute. So this is when uh, the BCNF have problem with. So let's take a look at the more examples of how it looks like and then how are we going to deal with it. Okay. This relation is actually in third normal form, but not in BCNF. Let's say we have a teach table with student, course, and instructor. So we have a student here, course here, and instructor here. And I have two FD, two functional dependency. I said that student and course determines instructor, and I have instructor determines course. So you remember the diagram, right? When I said like the prime attribute determines non-prime, and then you have non-prime that actually determines back to the prime. So you have student and course determine instructor, but instructor also determines course. So in this case, student and course is a candidate key for this relation. And the dependencies also follow the pattern that I just showed you. So this relation is in third normal form, but not in BCNF. All right. So a relation that is not in BCNF must be decomposed further. So to meet this property, let's see how we going to decompose it. So you have three ways to decompose it, right? So three possible ways are you can decompose like student instructor and student course is one way. Course instructor and course student is another way. And then instructor course and instructor student is another way. But there is only one good decomposition. It cannot be just any decomposition. Of course, you need to decompose them, but you need to select the right decomposition such that it does not have lossless, it does have lossless property, right? It does not uh, incur any additional data or loss of data. So all three decompositions will lose FD1. But we have to settle for sacrificing the functional dependency again. So we cannot sacrifice the non-additive property after decomposition. So out of these three, actually, the third one, instructor and course and instructor and students is actually the only way to decompose it. Why? Let's go back to this. I will take a look at it. I said that we should do instructor and course and instructor and student because of the functional dependencies here. Instructor and course, you can say that instructor actually determines course, right? So it means that instructor is a key in this case because just the instructor, you can tell course. So now, because it becomes key in FD2, you can take that key and then use it to decompose the table by maintaining that particular key. All right. So I use instructor on both sides, instructor here. And then I fix it by putting course there and student there. So you can decompose it using that super key to become the common key that on both of the decomposition sides. All right. So now if you want to compute, you can try that. But this is the only way when you join them back, they will not introduce additional data or loss of data. All right. Now, well, the question is that is every decomposition good or must be done? So basically, there are also some problems to consider when you are working on decomposition because some queries may become more expensive because you need to decompose them and then you need to join them back. If you need to join them back all the time, the efficiency on the performance or the performance of the execution can be slowed down because if you need to join them back and make sure that it is still good, then we call it what we consider it to be expensive. Also, given instances of the decomposed relation, we may not be able to reconstruct the corresponding instance of the original relation. So this is a must that you consider that you cannot have the problem of the lossless join, right? Or lossy join. So checking some dependency may require joining the instances of the decomposed relation. So this is also another expensive things to do. So the trade-off must be considered, among these issues and the redundancies. Of course, when you do the decomposition, you can tell that the redundancy will be minimal, right? All the reasons to, one of the major reasons to decompose is to reduce redundancy, but also to make sure that the least anomalies could happen with the tables. However, there might be a problem with the performances of the table, right? So there's a note on denormalization also. You normalize a table, but a lot of times, not a lot of times, but some of the times, once you know that uh, the performance is bad because you need to join this back all the time, you might consider the step called denormalization. So basically, to reverse you reverse the normalization project for some of the tables, all right? So you only do denormalization to improve performance. So in practice, the denormalization will actually speed up the queries, but it could drag down other things like the redundancy might be there, or the anomalies can also happen. So you have to really proceed with caution when you consider denormalization steps. All right. So finally, is it a good or a bad thing? For the normalization. Normalization is actually very, very, very good, and you must normalize the tables. But you have to consider it against the performances as well. So in some cases, we might not mind redundancy as much if the data isn't directly updated. For example, you want a big report that have to be used all the time, like you break down by semester or whatever report that has to be shown all the time. You can consider denormalization, and you can allow some redundancy there. Or in some of the warehouse projects, you could have many copies of the data, which actually introduce redundancy, but it may be necessary in that case. And also for data sharing, sometimes we may export data into some object-oriented or hierarchical format such that the data sharing can occur more easily and with higher performance. So, yep, with normalization, it is always done, but you can consider denormalization or not even not normal. You can allow some redundancy if it is needed. So basically, that is everything we need to talk about for today. So it's quite a lot, and I have half an hour left for any of the projects. That if you want to talk to me about the projects, you can. All right. Again, let me remind you that next week is the milestone number 2, and we'll post the example of the report uh, in my course view so you can take a look at the report. So basically, we expect to see the ER diagram, and then from ER diagram, you will have the tables, right? And then we don't expect normalization because I think you do not have enough time to work on normalization for the report next week. But do as much as you can. And then all the we'll have something called data dictionary, and we'll put the example for you. And then next, the following week would be midterm already. So midterm will be everything that we talked about. And I see one of the students asked me if you'll be allowed a cheat sheet. I'll consider it. I'll let you know next time because the exam is not out yet. So if you want a cheat sheet, I will have to make it a lot harder, right? So I don't know which way you want to go. So we can discuss it the next time. And no, let me take a look at the exam first to see whether or not you need a cheat sheet. All right. And then again, I would like to remind you about the discussions board here, that it will help you a lot. If you go back to the exercises, take a look at the key and then discuss it, and then take a look at what your friends do. So, you will learn from here and it will be useful for the exam. Because after the exam, after the midterm, these exercises will not be used anymore, right? So after the exam, let me go back to the schedule. So after the exam, there'll be a lot more hands-on with SQL. So the first week after the midterm would be SQL. Uh, and a lot of you talk about Superbase. So I asked the speaker to actually introduce Superbase among other things. And so also with NoSQL, it will be your ISE student who graduated a few years earlier. And he will come in and talk about, he's like a guru in this area. So these two will require a lot of hands-on in class. So it'd be a lot of fun. And then after that will be some of the lectures again. But yep, basically you'll be working on your project from there. All right. Okay. For the report, we'll give out the example today, the requirement and the example today. Right. We need to what? Yes. Yes. We'll give out the example. All right. Okay. Let me stop share.